Our second and last speaker for today is Paolo Saracco from ULB, Université Libre in Brussels. And he's going to talk us about globalization for geometric partial comodules. So welcome, Paolo. Take the stage.
Here I am, okay. I was supposed to be able, oh, very well. Can you see my screen?
Yes.
Okay, very well. Thank you very much. First of all, let me thank the organizers for inviting me here today, and let me also thank all of you for being here to attend to this talk. I'm very honored of being the last speaker before the summer, but I should start with a small disclaimer. I'm not exactly a category theory person. I'm much more from the algebraic side of the force, and I believe you will notice that, but I'm particularly fond of category theory, and I use a lot of category theory, at least as much as I can in my research. Now, as you can see from the title, the topic I would like to speak about today is this globalization construction for geometric partial comodules, which is part of an ongoing project with Jos Verkreus here at the ULB of Brussels. And the project is exactly aimed at studying these geometric partial comodules. Now, the main motivation for studying these objects is because they provide a good categorical framework where to deal with the very vast panorama of partial structures that we have nowadays. And I hope I will clarify this claim later on during the presentation. And since this question on the existence and uniqueness of a globalization is one of the relevant questions in the field, it seemed natural to us to begin by addressing the problem from the point of view of geometric partial comodules. I already beg the pardon. I know that somebody in the audience already attended a previous version of this talk. I'm really sorry. Probably you will get bored almost immediately. But anyway, since I'm still arbitrarily assuming that the audience is not particularly familiar with these partial structures, I will begin with a small introduction about partial actions of groups in a very hands-on way, so very classical, very algebraic approach, just to develop a bit of intuition. After, I will present finally these geometric partial comodules and our globalization theorem for them, which is particularly interesting both because on the one hand, it allows us to recover a number of already existing globalization results in the field, and on the other hand, because it provides necessary and sufficient conditions for the existence of a globalization, and not only also an explicit construction of the latter whenever it exists. And finally, we will test our globalization theorem on a number of examples. And if anybody has questions, please feel free to interrupt me any moment. Also, if I'm not speaking too quickly, because that's also another issue. But anyway, let's start with partial actions of groups. Very informally, these are actions of groups by partial bijections instead of global ones. A bit more formally, a partial action of a group G on a set X is a partial function from G cross X to X, where this G bullet X, it's something that you can interpret as the space of all the composable pairs, so all the GX, such that G is allowed to act on X. And we require this partial action to satisfy a number of properties that remember those of a global action of a group. So for instance, we want that the neutral element of our group is able to act on every element of the set and it acts as the identity. We want that whenever an element G is allowed to act on an element X, G to the -1 is allowed to act on the result, and the final outcome is the starting X. And last but not the least, we want our partial action to be associative whenever it makes sense to be. Now, just to give you a toy example to develop a bit of intuition about what is going on with these partial actions, let me take this pair of tangent circumferences And let me take as a group, the group given by the product of two copies of a circle group. I will allow the left-hand side copy, so all the elements of the form G1, to act globally on the left-hand side circumference by rotation around the center, and they cannot act on any element of the right-hand side circumference. All the elements from the second circle group, so all the elements of the form 1H, are allowed to act on the right-hand side circumference by rotation again around the center, and they cannot act on any element of the left-hand side. And now I still need to tell you what to do with the mixed elements. These are allowed to act only on 2 points of my object. One point on the left-hand side circumference is the unique point, such that if I rotate by G, I land into the intersection point, and I claim that its image is then the point that I obtain by rotating by H on the second hand circumference. And you may imagine that the other point is the unique point on the right-hand side circumference, such that if I rotate by H, I land into the intersection, and then I can further rotate by G. And this is the image of my point. So this looks like a bit exotic, I know, but if you think in terms of symmetries, this partial action is exactly giving us a sketch of our geometric object, because it's telling us that that it's composed by two parts. These two parts can be rotated, and these two components are tangent one to another, because I can take a point from one circumference, let it rotate, and let it move on the other circumference. So this kind of internal symmetry description of the object really make us understand that it's not a rectangle, for instance, but it's really composed by two circumferences tangent one to another. If you want something, less folkloristic, also remember that the Möbius group act globally on the Riemann sphere, but we can always restrict this action to the complex plane, and the resulting action is not global because of the vanishing of the denominator. And in fact, the Möbius group acts partially on the complex plane. And in fact, concerning this second example, this idea of restricting global actions to subsets is exactly the most important source of examples of partial actions. Namely, the idea is to have a big G set Y with a global action, look for a subset of Y, and restrict in a smart way our action to X. Since X is not necessarily stable under the G action, we cannot expect to have a global action again, but what we find can be proven to be exactly a partial action in the sense of the previous slide. And we call this the induced partial action from Y to X. And again, just to give you a toy example to keep in mind, let me take this nice torus. Let me take the same group as before, so the product of two copies of the circle group. The left-hand side copy now is allowed to act by rotation around the circumference of the centers of the torus, and the second copy is allowed to act by rotation of the torus around the vertical axis. This is a global action. Now let's assume I want to restrict it to these two black circumferences on the torus. It's clear that any element of the left-hand side copy of the circle group can act globally on the vertical circumference, but it cannot act on any point of the horizontal one. On the other hand, any point of the second circle group, any element of the second circle group can act on a point of the horizontal circumference by rotation, but it cannot act on any point of the vertical circumference. And then we have two distinguished points, which are still stable under the actions of an element of the form GH. For instance, we have a point on the vertical circumference such that if we rotate by G using the first copy, we land in the intersection. And then if we rotate by H, we are still on the horizontal circumference. And the same is happening for a point on the horizontal circumference such that after rotating by H, we land in the intersection. And so we can further rotate by G. And we are still in our subset composed by the two circumferences. Now, I'm sure you guess what I'm going to say in a moment. If we take these two circumferences and we draw them on the plane, we find exactly the exotic partial action I showed you at the very beginning. So two examples we have of partial actions. Both examples can be seen as induced partial actions. And then we have the question, the natural question, if this is always true. I mean, is it true that any partial action of a group on a set is in particular an induced partial action? This is exactly the philosophy underlying the globalization procedure. Given a partial action, we call globalization a global G set, which contains our carrier in such a way that the original partial action coincides with the induced partial action, as it happens, for instance, for the Möbius group acting on the complex plane, or the two copies of the circle group acting on the tangent circumferences. And we furthermore want, of course, our globalization to be universal, now in the sense of being initial, minimal among all the global G sets satisfying this property. And the important fact, which somehow lies at the bottom of all this globalization procedure, is a theorem by Abadi in his PhD thesis, in which he concretely proved that any partial action can be globalized. Actually, one can always construct this global G set here, where the global G action comes from the left-hand side factor. It contains X as embedded in the right-hand side factor, and the partial action on X is induced by the global action of G on this set. And just to close the circle, the Riemann sphere is in fact the globalization of the partial action of the Möbius group on the complex plane, and the torus is the globalization of the partial action of the two circle groups on the tangent circumferences. And with this, we close this small digression about partial actions of groups. But before moving to geometric partial comodules, let me conclude by saying that these are just the tip of the iceberg. As it happened for global actions of groups, partial actions are having a great fortune all around mathematics. So in the last 25 years, we experienced a true proliferations of partial structure all around mathematics. So we not only have partial actions of groups on sets, but also on topological spaces, algebras, commutative algebras, sister algebra, and so on and so forth. And quickly the investigation entered the realm of algebras. So nowadays we meet partial modules and comodules over of algebras, partial representations and co-representations, partial comodule algebras, and so on and so forth. I don't want to invest too much time in this. If you like, there's a nice survey by Dokuchaev in which he tried to collect all these known partial structures that we have nowadays. But I mean, I hope it's clear that we need a kind of categorical approach to these different but still similar partial structures. And furthermore, for almost all of these partial structures, we have analogs of the globalization theorem as we have for sets. The issue is that these globalization theorems are somehow strictly connected with the structure of the carrier of the partial action. So having a globalization theorem for one of these structures does not help in finding a globalization theorem for another. So we also need a framework where to deal with this globalization problem from a unified point of view. And this framework has been offered to us exactly by these geometric partial comodules, which have been introduced by Joost and his PhD student, Jaiwei Hu, a couple of years ago. They were aiming to describe partial actions of affine algebraic groups on affine sets, but we realized quite soon that these geometric partial comodules are flexible enough to allow us to recover a number of partial structures as those that I showed you before. And to convince you of this, let me tell you what these geometric partial comodules are. First of all, they can be defined over an arbitrary coalgebra in a monoidal category with pushouts, where very easily by a monoidal category simply mean a category with an associative and unital tensor product. And by the way, in what follows, I will always assume it to be strictly associative and unital, so no associator, no unitors, no non-trivial associator and unitors. And by a coalgebra, I mean an object with a co-associative and co-unital comultiplication. Now, if we have this, then a geometric partial comodule is a cospan of this form with an epimorphic lag that can we, the cospan, I mean, interpret as a partially defined coaction, which we want to be co-unital in the sense that these two cospans are the same up to isomorphism, where this has been obtained by push out. So that's why I need push outs in my category. And we want it to be co-associative in the sense that these two big cospans are required to be the same up to isomorphism, where again, all the squares have been obtained by push out procedure. I mean, this is simply composition in the category of cospans. And if you like, this is exactly applying the coaction twice, and this is exactly applying co-multiplication after the coaction. So this is really a co-associativity condition. And now once we have objects, of course, we want morphisms between them, and we can define morphisms of geometric partial comodules to be pair of maps in my underlying category, which make this shield type diagram to commute. And once we have them, then we can form the category of geometric partial comodules and their morphisms. But I promise you the flexibility of this notion, and the flexibility lies in the choice of the underlying category. So for instance, partial actions of groups turn out to be examples of geometric partial comodules in the opposite of the category of sets. But that's not all. By taking the opposite of the category of sets, in fact, we recover the partial actions of monoids. By taking the opposite of the category of topological spaces, we find partial actions of topological monoids on topological spaces. By taking either vec or vec op, we find partial comodules or partial modules over Hopf algebras. By taking the category of K algebras, we recover partial comodule algebras, and so on and so forth. We hope to be able to upload to arXiv soon a second preprint in which we deal with all these particular examples with a lot more, many more details than here. But we are here to speak about globalization, and in order to introduce globalization, we still need to be able to speak about induction. Again, as you surely expect, if we have a global comodule and we have now an epimorphism to some object in our category, then we can form this, the above span. We can consider the push out of the above span, and this induce a geometric partial comodule structure on our carrier X, which we call the induced partial comodule structure. And this is, in fact, just a reflect of what is happening for partial actions of groups on sets, because the induction that I showed you at the very beginning can also be interpreted, can also be described by saying, okay, we're taking the pullback in the category of sets of these two maps. So this is exactly the very same induced partial action that we have seen at the very beginning. And since now we're able to speak about induction, it's time to speak about the opposite construction, So it's time to speak about globalization. Given geometric partial comodule, we call globalization. Oh, by the way, I was forgetting something here. Something important, which is the fact that if I induce a geometric partial comodule structure, then the starting epimorphism becomes a morphism of geometric partial comodules. And the other important fact is that if this map here that you see obtained by the coaction of y composed with the projection on x, if this is monomorphism, if this is monic, then we say that y is co-generated by x. This is pretty intuitive, in particular if you see it's causing here. If this map is surjective, then it's clear that y is generated by x as a G-set. If G was an algebra and x a vector space, then it's clear that y is generated by the subspace x if this map is surjective. And here we are in the dual context. So if this is monic, then we say that y is co-generated by x as a comodule. And this was needed because I was ready to say that the globalization of a partial comodule is a global comodule together with an epimorphism, such that, first of all, the partial comodule structure is induced, the original partial comodule structure is induced by the global comodule structure of y. So this means that this diagram, which I will informally call the induction diagram, is commutative and it's a push-out square. And the second condition is that we want y to be universal in the sense now of being terminal among all the global comodules admitting a morphism of partial comodule, of geometric partial comodules to x. And whenever x admits a globalization, we call it globalizable, and we can consider the full subcategory of globalizable geometric partial comodules. So now the question becomes, when are geometric partial comodules globalizable? Because this is what we are interested in. And here is where our main result enters the picture. We prove that a geometric partial comodule is globalizable exactly if and only if, first of all, this equalizer exists in the category of comodules, which is providing the global candidate. And the induction diagram is a push-out diagram. So the partial comodule structure on X is induced by the global comodule structure on Y. And the important stuff, the important corollary, the cherry on the top of the cake, is that if these two necessary and sufficient conditions are satisfied, then Y is exactly the globalization of X. So we are really able to compute the globalization of a geometric partial comodule. And last but not the least, notice that this kappa here, it's the same kappa coming from here. One can prove that this is in fact the same as doing epsilon tensor identity of H after delta. And since it is the morphism of an equalizer, it is always monic. So the globalization is always co-generated by the carrier of the partial structure. This will be important in a moment.
So sorry to interrupt you, but what happens if I compute the globalization of the join of S1 and S1 as in the example? Do I get the torus or I get something smaller maybe, or bigger, I don't know.
In that case, you get exactly the torus. I mean, it's difficult to visualize. One can write down the algebraic computations with the two maps which are isomorphic, but very informally speaking, the idea is that to compute the globalization, you start with your geometric object, and you have to take the product of the geometric object and the group. The group was two copies of the circle group, so it's like taking the two circumferences. First, you rotate them in the three-dimensional space, so you have two parallel torus. Then you rotate still in the four-dimensional space, so you have a torus of toruses. And then that equivalence relation makes all the toruses to collapse on the very same torus, which is the globalization of the two. And more or less the same is happening with the Möbius group and the complex plane and the Riemann sphere. Okay, so now what's just the idea, the key observation underlying this theorem is the fact that, well, first of all, any global comodule is geometric partial comodule. This we already implicitly used when I say that the epimorphism P was a morphism of geometric partial comodules. And the second one is that for any geometric partial comodules, we always have a bijective correspondence between morphisms of geometric partial comodules from a global Y to our carrier X, and morphisms of global comodules from Y to the domain, this domain here of the two maps I'm computing the equalizer. So morphism of global comodules, which equalizes the pair of morphism we have seen a moment ago. So this just to explain why, if we are able to compute the globalization, then this globalization is in fact a right adjoint to the fully faithful functor that realizes every global comodule as a geometric partial comodule. So this is just to close the picture about this globalization construction. And now it's time to test our globalization construction on a number of cases. And what better example to start with than partial actions of monoids, which are the one that we know best for the moment. In the opposite of the category of sets, geometric partial comodules are exactly partial actions of monoids. And the category of sets is a really nice category because independently on the monoid, the two necessary and sufficient conditions are automatically satisfied. So our globalization theorem allows us to recover a well-known theorem by Megrelishvili and Schroeder, in which they concretely perform the globalization of a partial action, of a monoid. And this is also consistent from the point of view of the concrete realization, because their globalization can be computed as the co-equalizer of the pair of arrows we were considering in our globalization theorem. And furthermore, if we restrict further the attention just to partial actions of groups, we also recover Abadi theorem I showed you at the very, very beginning. Good. Our theorem is working very well, at least for sets. Let's see something a bit more complicated. Let's see what happens for topological spaces. Now let me start from the bottom where we want to go. Here again, we have a theorem by Abadi saying that topological partial actions of groups are always globalizable. Now, the first difference from the context, from the framework of sets, is that geometric partial comodules are more general than topological partial actions. In fact, we even don't have a full globalization theorem for geometric partial comodules in TOPOP, because we have an example of a geometric partial comodule which does not admit any globalization. Now, I don't want to sink into the details of this example. It's particularly artificial. Briefly, the idea is to take an honest, discrete action of a group on a set, topologize everything by putting in discrete topology everywhere, then construct the bullet by taking the original product and simply endowing it with the discrete topology. This is a very artificial way of converting this span here into a geometric partial comodule. This square is the induction square, and it's clear it cannot be a pullback. So this is an example of a geometric partial comodule, which is horrible enough to not admit a globalization. But nevertheless, if we just restrict our attention to the topological partial actions of interest for the literature at least, we recover exactly Abadi theorem. So Abadi result becomes a particular instance of our globalization theorem in the setting of topological partial actions. Very good. Okay, the test for the moment is passed, but since we have new objects, new theorems, we want to do some new mathematics. So let's try to do something new. Let's see what happens with geometric partial comodules in abelian monoidal categories. Again, this is a very favorable framework because 1.5 out of the 2 necessary and sufficient conditions are always satisfied. Namely, in the underlying category, we can always compute the equalizer of the 2 arrows we are interested in. This turns out to be exactly the pullback of the cospan defining the partial comodule structure. The induction square is so nice that it is not just a pullback square, but it's also a push-out square. So the only thing we need to take care of is the comodule structure on the equalizer. Because in our theorem, the equalizer is computed in the category of comodules, so it has a comodule structure on its own. Here is computed in the underlying category, but if we are lucky enough of being working with a coalgebra such that the category of comodules admits equalizers, and these are preserved by the forgetful functor, then our globalization theorem tells us that any geometric partial comodule over this coalgebra is globalizable. We have sharper results than this, but this is the easiest one to apply, in particular because, for instance, over vector spaces, this property of coalgebras is always satisfied for any coalgebra. Over modules over a commutative ring, or even modules over a ring, over a K-algebra if you prefer, this is always satisfied. It is always satisfied if the coring is flat as a module over the underlying ring. So, I mean, there are a number of contexts of interest for which this theorem is always satisfied. And for instance, for vector spaces, it allows us to completely fully characterize geometric partial comodules. So, well, actually also geometric partial modules over an algebra. These are global modules with a chosen generating subspace where the carrier of the partial structure is the subspace. And for geometric partial comodules over a coalgebra, these are global comodules with a chosen co-generating quotient space, where again, the carrier of the partial structure is the quotient space. And if we further apply this theorem to a number of globalization results or a number of frameworks as those I spoke about at the very beginning, then we start recovering a number of globalization theorems as I promised you at the very beginning. So for instance, for partial modules over Hopf algebras, we recover the standard dilation that has been introduced by Alves, Batista, and Yost a few years ago. For partial representations of finite groups, we recover exactly the globalization that we used with Michele D'Adderio and William Otkit in a recent preprint. For partial comodules over Hopf algebras, we have a completely new globalization which was not existing before. For partial commodule algebras, we have a brand new globalization, which in this case, this is the first case in which our globalization does not coincide with a globalization already existing in the literature, because the enveloping coaction of Alves and Batista, well, essentially because it satisfied the dual universal property in this case. They ask it to be minimal with respect to inclusion. We ask our to be terminal with respect to having a morphism to the carrier. So they were expected to be different. And now, last but not the least, let me show you a final application of our globalization theorem, if you like, which more than a result, I believe should be called a remark, but it's interesting anyway. So again, we work with an abelian monoidal category. This time it's the category of k-linear representations of some groups, the group you prefer. We consider the group algebra inside this category. Since the group algebra is a Hopf algebra, it becomes a coalgebra therein. So we can consider global comodules and geometric partial comodules over this coalgebra in the category of representations. It's already known that global comodules in this case are graded representations. So we call partially graded representations the partial comodules over this coalgebra. And thanks to our globalization theorem, together with Larson's Wheeler theorem, we are also able to completely describe these geometric partial comodules because they are only and only of this form. So they are quotients of the free gadget by a certain submodule with the geometric partial commodule structure obtained by induction. So the idea is that our globalization theorem tells us that they are all and only induced geometric partial commodules, so they are all globalizable. And Larson's Wheeler theorem tells us that any Hopf module over a Hopf algebra is of the free form. So it's the Hopf algebra tensor by a vector space. And the observation, if we like, that I was interested in is the fact that thanks to this description, structures of partially graded representations on the base field up to isomorphism are in bijective correspondence with linear characters of the group. I mean, it's clear that any linear character of the group can be, how to do this? Any linear character of the group can be transformed into epimorphism of modules from kg to k. So it induces a geometric partial commodule structure on K, but the important fact here is the converse. Any geometric partial commodule structure via globalization becomes, give rise to, let me say like this, a linear character of the group. And in fact, up to isomorphism, the two are really the same. And that's everything I wanted to tell you. Probably I'm even 10 minutes in advance, isn't it?
There is no problem. That was very good. And
it's the last one. For those of you who are already in vacation mood, in summer mood, we can simply enjoy the nice weather. For once, even in Brussels, there's a nice weather outside.
Amazing. I was there for a few days. You remember there wasn't a single day without rain. Terrible. Anyway, we have plenty of time for questions. First of all, thank you. That was a very nice talk and very interesting. I knew everything, but I enjoyed it again. So thanks. Okay. You're free to, well, of course, let's thank the speaker silently. And time for question. Anyone wants to chime in?
I have a probably tangential question. So
yes, please.
In the conditions for globalization, there was one existence of an equalizer, and then the second was that something has to be a push out. And what looks interesting to me is what happens if the equalizer exists, but that other diagram isn't a push out. So it looks as though what will happen is that the actual push out is sort of a co-reflection of the original partial structure to a globalizable partial structure. And then it looks interesting in various cases when not everything is globalizable. What needs to be done to a partial structure to make it globalizable? What does that push out, or in reverse categories, pullback, what does it actually look like?
If I understood the question properly, the problem is not in this case. Okay, the issue in this case is that if we really want the globalization, we want that the original partial action or partial coaction on the carrier is induced by the global one. And this push out condition is exactly as it was happening for sets. Okay, it's exactly having the push out is telling me that the partial structure is induced one. If I have the square, but the square is not a push out or a pullback, then I can induce a new partial structure on the carrier. And the original one is completely lost. I don't know where it was coming from. The new one, I know it's an induced one. It's more or less what was happening. Where did I put the topological spaces? Here.
Yeah, with the getting the wrong topology.
Yes, yes.
Corrects the topology. But of course, the push out comes with a morphism to the original thing because it is a push out. And so in this case, it's just a nice continuous map from discrete to indiscrete. But in general, it may be something more interesting. So it's essentially saying, given this not globalizable thing that you start with, you get a globalizable thing with a morphism to it. And so this is one example, but are there more interesting examples, perhaps in some of the algebraic cases? What sort of correction of the structure is being done by taking that push out, and how does that map to the original structure work? So at least I guess I should say I'm not asking this so much as a technical question, but as an attempt to improve my intuition of what's going on.
On the one hand, the correction given by having the push out is throwing away redundancy. Let me tell in this way. In principle, imagine again the case of the torus. I can start with a sphere in the center of my space and the torus around, and have the two very same actions, the very same action I had before. I can restrict my action to the two circumferences on the torus, and I have the partial action on the circumferences. Taking the globalization, so asking for the push out condition tells me that I can forget about the sphere. The sphere was not giving any contribution to the partial structure. Algebraically, it's very difficult to find pathological examples as this one, because in this case, in the topological case, I'm not throwing away any redundancy. I'm simply saying, oh, you took the wrong topology. You need to correct your topology. From the algebraic structure, due to the very general statement that we have for abelian monoidal categories, is very difficult to provide an example of an algebraic structure that cannot be corrected by taking the push out or the pullback. We have an example essentially constructed on localization. So we construct a geometric partial comodule by localizing the ring of polynomials at the inverses of the indeterminate. And that is, again, a non-globalizable partial comodule structure, which cannot be even corrected in this case. So there's nothing in between. That square is the unique square you can draw, and there's no way to correct it, not like here that we adjust the topology and finally we arrive at the correct object. In that situation, there's no way to correct the picture.
Okay, good. Okay, thank you.
You're very welcome.
Any other questions? I think I have a couple, but of course,
I
I'll
have
give precedence.
one comment maybe. So I'm sure Fosco told you that there is a connection with our paper that is quite new.
We are working on that, yes.
I think there is a connection.
Yes.
But I wanted also to mention another paper, which I think is I mean, the kind of results that our work can give is something like the category of modules is locally finitely presentable. This is the kind of results one can give. But there is, about the globalization, we don't do much. Or at least in my opinion, it's not in our paper. But I think someone did something in this direction, and there is a paper by Kobeck and Reiterman. I will put it in the chat. I put it in the chat. And in this paper, they defined the notion of partial algebra for a monad. And then among the other things, they globalize partial algebras. And so they proved that under some assumption, you have globalization results for partial algebra. If I remember correctly, I mean, the paper is not the most readable of the work, but if I remember correctly, they show that under some assumption, you can globalize partial algebras. And this monadic approach is more natural than the one of our paper, because it's evident that in your context, you start from something that would like to be global, and you unglobalize it. And because you have already a monoid in a sense that would like to act globally but doesn't. Instead, in our paper, you don't really have this attachment to something that is already very global. So instead, in this paper of Kobeck and Reiterman, they start from a monad, and then they study two algebras for the monad and partial algebras, and then they relate them. So it's more in the spirit of what you're doing, I think. So maybe give a look to this paper, that's all.
Absolutely, thank you very much. Yes, I believe I understand what you were saying, because in fact, it's something I was observing. You have partiality everywhere, while in our setting, really the object acting is a global object, and the partiality is only on the carrier of the action. And by the way, just to close the comment, you can also try to do, instead of the globalization, as I showed you at the in this very presentation, there's also another approach. Here, we are taking the carrier and we are modifying the carrier to convert it into a global something. The other approach is to move the partiality from the carrier to the acting object. So for instance, the partial modules over a Hopf algebra are the same as global modules over a Hopf algebroid. So that's the other side of the picture. But I will surely have a look at the paper you posted in the chat.
Yes, maybe I can also add something on this, because of course Ivan knows like what you're correct, what we do in the paper doesn't touch this globalization problem. For the moment, I think that there's a very neat way to describe partial actions in terms of, well, more or less, instead of a functor from the group to set, because of course actions are presheaves. In this case, they are restriction presheaves, where you fall into the restriction category of sets and partial functions, or whatever you like, your preferred power of k for some k. And these functors are lax, in the sense that the laxity cell give you for free, just because they are laxity cells, some of the conditions in the initial definition. And the other comment that I think it's fruitful, and I am in the process of investigating Paolo and Induced, is that this procedure of discharging the partiality over, as Paolo said, you can think of a partial action of a group as a total action of a groupoid. So this really seems like the modified Karoubi envelope construction that we employed. Because you see, when you map into power of something with the restriction functors, that's exactly a genuine functor from the Karoubi envelope, that K of T, that modified Cauchy completion with fancy bells and whistles. Anyway, this is very technical. I don't want to bore the audience to that. I have a naive question, which is probably boring, but probably very simple to answer and will avoid us a few minutes of discussion later. And a more conceptual or, well, broad, wide-ranging question. What do you prefer?
Let's start with the broad, wide-ranging question.
Okay. If there is a possibility I didn't hear this example, but I think in your list of possible examples of partial actions, but I think another source of interesting examples of group actions comes from algebraic topology. I'm thinking about the fact that the fundamental group of a space acts on the fibers of a covering map. And you get an extremely interesting theory from that because you get a Galois theory. So is there something interesting in the partial analog of the Galois theory of coverings or even Galois theory of fields?
I'm sure it is. One of the original questions that led to this globalization procedure was exactly Galois theory for partial actions on commutative algebras. So probably the second most used globalization theorem is when you have partial actions of groups on commutative algebras, and the authors, I think they were Dokuchaev and Excel, probably. They were trying to perform Galois theory for these partial actions of groups on rings, and there the globalization theorem was somehow the key of the success of the procedure. So I'm super sure that, well, not super sure, but I'm confident that there could be something interesting in trying to study partial Galois theory for whatever, not only in algebraic topology, but also ordinary Galois theory of fields. I don't know if something has already been done.
But you don't know anything in the direction of algebraic topology. I'm thinking about not only Galois theory, but maybe even more refined results, like, forgive me if I quote the result wrong, but I think it's true that the higher homotopy groups of a space are modules over the pi1, something like that. Okay, yes, Ivan is nodding, so it's true. Or the fact that you are often interested in the case where this action is trivial, or even this action is nilpotent. So nilpotent spaces are very well behaved for an homotopy theory, from an homotopy theory point of view. And what about nilpotent partial action? What can I say about obstruction theory? What can I say about all the fancy stuff that algebraic topologists use group theory for? Anyway, this is this is not a question. It's nothing precise. It's just a suggestion.
And in fact, I cannot give any precise answer because I honestly no idea.
Okay.
But thanks for pointing it out. If you have half a day to explain to me all these things that you mentioned.
I quit that stuff. I was unable to understand it, even if I did 24/7 for quite a long time. Anyway, the other question is way simpler. And it is a question that I was trying to push on Joost and you. The bullet construction, G bullet X. No, it's not.
It's lax monoidal.
Ah.
In the best case that we have presently, it's lax monoidal.
Okay, Joost, but at least it has a universal property of some kind, right?
That is part of your question that I didn't understand, because the bullet is part of the data. So it's it's essentially the subset of the composable pairs. It's something that you give. Okay, in principle, it's something that you give together with it's part of the partial action, coaction, whatever. It's not something that you recover out of that. But
probably he is a certain pullback equalizer in a category where in a category of actions, because the partial action is a certain map of some kind. And I think I can explicitly write down the equalizer. Anyway, this is probably as boring as my initial question. So I just wanted to put you in a corner and ask you.
I know that Yost and Jawei worked for a long time on this bullet because they wanted to, now I don't remember the way, they wanted to describe Hoff modules. So they were needing to have an underlying monoidal category and consider the coalgebra as a coalgebra inside, so a bialgebra as a coalgebra inside this monoidal category. And I know that they didn't manage to, but there's a way to convert the bullet into a tensor product between geometric partial comodules, but it's not associative in the classical sense. It's just lax associative, as the Takeuchi cross product, more or less.
Okay. Okay, that's all from me.